After a few months, the concrete blocks had become caked with dirt and needed to be cleaned with a pressure washer. Additional equipment was brought in, the most significant being a Kubota MX5200 tractor. This significantly reduced the amount of manual labor required, especially given the amount of concrete and block that needed to be moved. Unfortunately, the tractor could not lift a full pallet of block or concrete but could do about 80%, requiring a few rows of material to be moved off the pallet. Pouring mixed concrete into the front bucket was a huge improvement in efficiency, allowing the cells to be filled with concrete quite easily. With the walls nearing the full height, a layer of asphalt emulsion sealer was applied to the exterior to add a waterproof seal. The top of the basement would be constructed of steel and covered with concrete. This would create a fireproof barrier as a countermeasure against the ever-present danger of wildfire. The Kubota tractor was essential for moving the near 200-pound steel plates and steel I-beams and made an excellent platform for cutting steel on. While 4-foot by 8-foot steel plates were ordered, they were slightly larger than these dimensions, requiring additional cutting. I used a T-post as a guide for the plasma cutter to ensure a straight cut. The I-beams required holes to be drilled to attach to the anchor bolts. A step drill bit would be the correct tool, but I used a less efficient bimetal hole saw. 4 key pieces of equipment were acquired for the metal work. The Furman-powered dual-fuel generator 7,500 running watts, Hobart Handler MIG welder, Makita 3-horsepower 5.2-gallon air compressor, PrimeWeld 120-volt plasma cutter with non-touch pilot arc. The 5 CFM requirement of the plasma cutter meant a powerful air compressor was needed. To my surprise, the generator would not run both the plasma cutter and air compressor at the same time. After reaching out to technical support, I learned there is a 3.5% loss of engine power for every 1,000 feet above sea level. At my elevation of 5,500 feet, that turns out to be a 19.25% loss of power. The next stage was lifting the heavy steel I-beams into place. A task the tractor's backhoe made easy with the aid of tow straps. The 20-foot I-beams were cut to 16-foot sections, with the 4-foot remainder being used for cross-bracing. The utility trailer made it easy to move equipment and switch from cutting to welding. Anchor bolt holes were drilled with an SDS Max Makita hammer drill. The tractor once again made removing excess block easy with the backhoe and straps. The 4-foot I-beam sections were notched to fit between the I-beams running the entire span. This made welding easier as the beams simply slid into position. These cuts were made with an angle grinder, as these cuts were more precise and clean compared to the plasma cutter. My early welds were rough, but I would gain experience and skill over the hundreds of hours this project required. In the meantime, I decided to compensate with the sheer quantity of welds. I quickly learned how the heat from welding causes metal to distort and the importance of tack welding. The steel plate should have had angle iron spanning the width welded to the underside for support. Once the I-beams were welded and secured, 2x6 lumber would support the steel plate as it was slid into position. Then the wood supports were removed and the welding could begin. I did 6-inch welds around every 8 to 10 inches. I learned to leave a small gap between steel plates to allow room for the weld material. I also came to realize a stick welder would have been a better idea than a MIG welder in this application due to the thickness of the metal. My rigid knee pads were a must, as I was spending 12+ hours a day on my knees welding. I would wake up at 4 a.m. to start the day and discovered the below freezing morning temperature would have a noticeable impact during welding. I was having issues with the Hobart welder wire feed jamming. At first I thought it was due to flinching forward at the start of the weld, which would cause a wire jam. However, it turned out the feed wheels were slightly out of alignment and needed to be adjusted. I also learned certain flux core wire brands splatter a lot more than other brands. I ended up needing to upgrade to a heat-resistant cowhide leather jacket, as my Carhartt flame-resistant jacket could not withstand the splatter during overhead welding. The final row of masonry block required custom cuts to allow room for the I-beams. An angle grinder with a masonry blade was used for these cuts. I had several angle grinders to save time on switching attachments as they were used for so many tasks. I had a wire brush attachment for removing rust and other contaminants before the weld, as well as a twisted wire brush for removing slag after. One of the best attachments was the Walter Enduro Flex flap disc. The 7-inch angle grinder was absolutely amazing when it came to cutting metal. A huge upgrade compared to the 4-inch grinder. With the steel plate welded, it was time to install an access hatch. I went with the largest prefabricated roof hatch I could find. Looking back, it would have been better to use a floor hatch, but the best option would be to craft one due to exorbitant cost of prefabricated units. Welding the hatch's thin metal to the thick steel plate was a new challenge. Next, I placed additional welds underneath the steel plate to further secure it. For ventilation and utilities, I tried to drill holes through the steel plate with the bimetal hole saw kit. However, the steel was too thick. I had to use the plasma cutter, resulting in jagged, uneven holes. I cut 2-inch holes for utilities and 4-inch holes for ventilation. Looking back, I should have just made the holes in the masonry wall instead. When not in use, I covered the structure with a heavy-duty tarp to protect from rain. However, the basement still flooded and I used a submersible water pump to remove the water. Next, I applied a layer of asphalt emulsion. In retrospect, Rust-Oleum Rusty Metal exterior oil-based primer would have been a better choice, although more expensive. Next, we prepared to pour a 4-inch layer of concrete. Wood forms were held up by wood stakes. Rebar formed, we split the pour into 3 sections while leaving the rebar untouched. We placed plastic sheeting down, but this turned out to be a mistake as it traps water. 2-inch ABS pipes were inserted into the holes cut for utilities. However, it did not fit and had to be enlarged with the plasma cutter. After the 2-inch and 4-inch pipes were secured, the gaps were sealed with silicone. Rebar was bent at 90-degree angles to anchor into the block wall vertically. The rebar initially formed 24-inch squares, but I upgraded to 8-inch squares to ensure stability. The day of the pour, we set up a concrete mixing station to fill up the tractor bucket. With a 3-man team, there was a constant flow of concrete being mixed, poured, and finished. Breaking the pour into 3 sections made leveling the concrete easy. Using a magnesium float, followed by a steel trowel, created a smooth finish. With the first section done, it was onto the next, and we completed 2 sections in the same day. The tractor was a huge help, moving 8 cubic feet of concrete per trip. After the concrete lost its sheen, it was time to apply a concrete curing agent. This is especially important in the hot, dry Arizona summer. A few days later, it was time to work on the final section. An 8-inch rebar grid was formed and suspended 1.5 inches above the metal using concrete block scraps cut to size. The upgrade to 2 Yardmax 4 cubic foot concrete mixers significantly improved the workflow as it allowed the tractor's bucket to be completely filled each trip without waiting. 250-gallon water totes were brought in by trailer and allowed for 5-gallon buckets to be filled without the need for a water pump. The hardest part of mixing is ensuring the concrete is as thick as possible for maximum strength. I recommend wearing a mask as the mixing process generates a lot of dust. It is important to keep in mind that not all curing agents create a waterproof finish. Cheaper ones will generate a wax-type coating that will wear off with time, preventing the immediate application of a waterproofing agent but leaving the concrete vulnerable. The last step was to apply asphalt emulsion to the concrete to prime it for the waterproof membrane that would be applied after. With the concrete finished, I could finally admire all the work. It was a long journey, and there was still a lot to do, but at least I could finally start enjoying the result of my labor. Thank you for watching.